Hello, everyone. Today I'm going to be presenting some work I've been doing with Justin at Cornell. So just to bring some of the ideas that the reason why we were thinking about these things. So some people have used ideas from separation logic to reason about probabilistic independence in the context of a first-order imperative programming language. So the questions we want to answer in this work is, can we use some of these ideas in a high-order functional setting? And can we use a type system that encodes their reasoning principles inside the type system itself without needing to go to an outside logic? And for those who are familiar with separation logic, they might think that there is an easy way of doing this by using bunch typing, which is the Curry-Howard version of separation logic, and has two distinct pairing operations and two distinct arrow types. And the way to give semantics to these things is fairly well understood. It's by using Cartesian closed categories with a separate symmetric monoidal closed structure over it. The problem with this approach is that these models are extremely rare in the real world, and there are no known models for it that can handle probability. So we take a slightly variant of this work, of this language, by using two different languages. We have a first language, NI, where resource sharing is allowed. We have a second language, I, where sharing is not allowed, and we have a functorial layer between these two languages, between the language NI into the language I. And thinking more about the syntax, what this means is that there are two separate typing judgments, one for the NI language and one for the I language. And there's a type constructor M in the I language, which models this functor between these two languages. The categorical semantics for this is fairly simple. There's a category C, which is a copy-delete category, which is just basically a category that allows you to reuse values. There's a symmetric monoidal closed category L, where sharing resources won't be allowed. And there's an applicative functor between these two categories. And for those who don't know what that entails, what we're interested in is basically that it has this operation. It has an operation that takes two independent distributions and outputs their joint distribution. And what's really good about this setting is that there are many actual models out there. So there are models based on familiar models of linear logic, such as probabilistic coherence spaces. There are for algebras for commutative monads, which are many probability monads out there. So this is a very general framework that works for different probabilistic semantics. And it's also the more general version of affine separation logic. And we also show a theorem that basically justifies our claim that this is a language for reasoning about probabilistic independence, which says that if you have a program T with no free variables of type m tau1 and m tau2, then it can be factored as two different morphisms, which corresponds to the marginal distributions, such that the semantics of T is their joint distribution, is their product distribution. Thank you.